On January 15, 2022, scientists at monitoring stations across the Pacific Ocean detected something that shouldn't have been possible. Pressure sensors in New Zealand, Fiji, and as far away as Alaska began registering a shockwave so powerful that instruments initially couldn't determine its origin. Within minutes, satellite imagery revealed the source. Hunga Tonga Hunga Haʻapai, a submarine volcano in the Kingdom of Tonga, had just produced the most powerful volcanic explosion ever recorded by modern instruments. The eruption sent an ash plume soaring 58 kilometers into the mesosphere, higher than any volcanic column in the satellite era, while generating a pressure wave that would circle the Earth multiple times over the next 6 days. But how exactly did this underwater volcano, which had been showing signs of unrest for weeks, suddenly unleash an explosion equivalent to hundreds of nuclear weapons? How did it generate a tsunami that reached heights of 15 meters in Tonga and was detected as far away as the Caribbean Sea? And why did this eruption exceed every previous modern volcanic event in recorded history, forcing scientists to completely reconsider what submarine volcanoes are capable of? Watch closely, because the Hunga Tonga eruption didn't just break records, it revealed that Earth's most dangerous volcanoes might not be the towering stratovolcanoes we've studied for centuries, but the hidden calderas lurking beneath the ocean's surface. December 20th, 2021, nearly a month before the catastrophic eruption, the first signs of volcanic unrest appeared at Hunga Tonga Hunga Haʻapai. Steam and ash began venting from the caldera as magma rose through the volcanic conduit beneath the seafloor. For geologists monitoring the volcano, this wasn't entirely unexpected. The volcano had erupted before, in 2014 and 2015. Creating new land that connected two previously separate islands, Hunga Tonga and Hunga Haʻapai, into a single landmass. But as December turned to January, the activity intensified. Ash plumes grew taller, reaching several kilometers into the atmosphere. Volcanic lightning crackled through the eruption columns as superheated particles collided. Local residents reported hearing continuous rumbling and witnessing glowing lava fountains during nighttime hours. Hunga Tonga Hunga Haʻapai sits along the Tonga-Kermadec subduction zone, where the Pacific Plate dives beneath the Indo-Australian Plate at a rate of approximately 24 centimeters per year. This tectonic setting creates one of the most volcanically active regions on Earth, with over 200 submarine volcanoes dotting the seafloor between New Zealand and Tonga. What made this particular volcano exceptionally dangerous was its unique geological structure. The volcanic edifice rose from a depth of nearly 2,000 meters below sea level, with its caldera sitting just 150 meters beneath the ocean's surface. This shallow depth created the perfect conditions for what volcanologists call phreatomagmatic eruptions, where seawater interacts explosively with rising magma. Throughout late December and early January, magma continued ascending through the volcano's plumbing system. The magma was dacitic in composition, meaning it was highly viscous and gas-rich, the exact type that produces the most violent eruptions. As it rose, dissolved gases, including water vapor, carbon dioxide, and sulfur dioxide, began exsolving from the melt, creating immense pressure within the volcanic conduit. Meanwhile, seawater that had infiltrated cracks and fissures in the caldera was being superheated to temperatures exceeding 1,200 degrees Celsius. By January 14, 2022, the volcano had entered a critical phase. Multiple vents were actively erupting, sending near-continuous ash plumes into the atmosphere. Satellite imagery from NASA and the Japanese Himawari 8 satellite showed a persistent volcanic cloud drifting westward. Tonga's government, while monitoring the situation, had seen similar activity in previous years without catastrophic consequences. There were no evacuations ordered for the main islands, though the immediate area around the volcano remained off-limits. Beneath the surface, however, the conditions were reaching a tipping point. The magma chamber, located approximately 5 kilometers below the seafloor, was being rapidly replenished with fresh, gas-rich magma from deeper sources. The overlying rock and seawater created a natural pressure seal, preventing gases from escaping gradually. January 15th, 2022, 4:15 p.m. local time. The catastrophic phase of the eruption began without warning. In a matter of seconds, the fragile balance between rising magma pressure and the confining weight of overlying rock and seawater collapsed. The initial explosion breached the caldera floor with such violence that it instantly vaporized millions of tons of seawater, creating a superheated steam blast that punched through the ocean surface. The eruption column shot upward at speeds exceeding 4 meters per second, reaching the stratosphere in less than 3 minutes. What happened next would be captured by multiple satellites orbiting Earth, providing unprecedented real-time documentation of a volcanic cataclysm. The Himawari 8 satellite, positioned in geostationary orbit 35,786 kilometers above the equator, was taking images every 10 minutes. Its infrared and visible light sensors recorded the eruption plume expanding outward in a near-perfect circle, growing from 5 kilometers in diameter to over 260 kilometers in width within just 30 minutes. The GOES West satellite operated by NOAA captured similar imagery, showing the eruption column climbing higher and higher, eventually penetrating the mesosphere at an altitude of 58 kilometers, more than twice the cruising altitude of commercial aircraft and higher than any other volcanic plume in the satellite record. The blast itself was heard as far away as Alaska, over 9,000 kilometers from the eruption site. Residents in Fiji, 780 kilometers away, reported hearing what sounded like distant explosions or sonic booms. In New Zealand, located 2,300 kilometers to the southwest, pressure sensors at weather stations detected sharp spikes in atmospheric pressure as the initial shockwave passed overhead. But it was the visual spectacle that truly captured the eruption's magnitude. The expanding ash cloud created an umbrella-shaped canopy that blocked out the sun across hundreds of kilometers of ocean. Volcanic lightning erupted continuously within the plume as billions of ash particles collided, generating static electricity on a scale rarely witnessed. The eruption produced an estimated 400,000 lightning strikes in just the first few hours. Within minutes of the main explosion, something extraordinary began appearing on barometric pressure sensors across the Pacific region. A massive atmospheric pressure wave was racing outward from Tonga at approximately 1,100 kilometers per hour, the speed of sound in air at sea level. This wasn't a sound wave that humans could hear, but an infrasonic pressure pulse powerful enough to be detected by specialized instruments designed to monitor nuclear weapons tests. The Comprehensive Nuclear Test Ban Treaty Organization operates a global network of infrasound sensors specifically designed to detect atmospheric disturbances. As the pressure wave expanded outward from Tonga, these sensors lit up in sequence. Stations in Fiji detected the wave first, followed by sensors in Australia, New Zealand, Japan, and across Southeast Asia. But the wave didn't stop at continental boundaries. It continued propagating across the entire globe. Meteorological stations in Europe began detecting anomalous pressure spikes approximately 8 hours after the eruption. Weather balloons launched from the United Kingdom registered the passing shockwave as a sudden jump in atmospheric pressure readings. In North America, pressure sensors from Alaska to Florida recorded the disturbance as it swept across the continent. Amateur weather enthusiasts with home barometers watched in real time as their instruments registered sharp pressure changes, many posting their readings online and contributing to a crowdsourcing effort to track the wave's progress. What made this pressure wave truly unprecedented was its persistence. Most atmospheric disturbances dissipate after traveling a few thousand kilometers due to friction and dispersion. But the Tonga shockwave was so energetic that it circled the Earth not once, but multiple times. Scientists documented the wave making at least 4 complete circuits around the planet over the following 6 days, with each passage becoming progressively weaker but still detectable. Researchers at the University of Bath in the United Kingdom analyzed barometric data from hundreds of stations worldwide and calculated that the eruption released energy equivalent to approximately 15 megatons of TNT, making it comparable to some of the largest nuclear weapons ever tested. While the atmospheric shockwave raced across the globe, a far more deadly threat was spreading across the Pacific Ocean. The violent displacement of water caused by the submarine eruption generated a tsunami that propagated outward in all directions. But this wasn't a typical tsunami caused by undersea earthquakes. The Tonga tsunami was created by multiple mechanisms acting simultaneously. the direct displacement of water by the eruption column, the collapse of the volcanic edifice, and remarkably, the atmospheric pressure wave itself pushing down on the ocean surface as it traveled. Within minutes of the eruption, tsunami waves began slamming into the Tongan Islands. The closest inhabited island, Tonga Tapu, located approximately 65 kilometers south of the volcano, was struck by waves reaching heights of up to 15 meters in some locations. Coastal villages were inundated, homes destroyed, and infrastructure damaged. Communication cables connecting Tonga to the outside world were severed, leaving the nation almost completely cut off. The first reports that reached the international community came from Tongans living abroad who lost contact with family members. Across the Pacific, tsunami warning centers scrambled to assess the threat. The Pacific Tsunami Warning Center in Hawaii issued alerts for coastlines across the entire Pacific Basin, from Japan and the Philippines to the west coasts of North and South America. But forecasting the tsunami's arrival proved exceptionally difficult. Traditional tsunami models, which rely on seismic data from undersea earthquakes, couldn't accurately predict waves generated by volcanic explosions and atmospheric pressure pulses. In Japan, tsunami waves up to 1.2 meters high struck the coast, prompting evacuations in low-lying areas. In California, harbor surges damaged boats and docks in Santa Cruz and other coastal communities. Even the Caribbean Sea, on the opposite side of the planet, registered measurable tsunami waves, demonstrating the truly global reach of the eruption's effects. Tide gauges in the United Kingdom detected sea level changes attributed to the pressure wave pushing on the ocean surface thousands of kilometers away. In the days following the eruption, the true scale of the catastrophe began to emerge. When communication was finally restored to Tonga through satellite links, the damage reports were devastating. 3 people in Tonga had been killed by the tsunami, 2 elderly residents who were unable to evacuate in time, and a British national. An estimated 84% of Tonga's population, roughly 1,000 people, had been affected by ashfall, tsunami waves, or both. Entire villages on the islands closest to the volcano had been obliterated, with nothing remaining but foundations and debris. The capital city of Nuku'alofa was blanketed in toxic volcanic ash, contaminating water supplies and rendering the airport unusable. International relief efforts were hampered by the damage to the undersea communication cable, which took weeks to repair. Meanwhile, scientists around the world were analyzing data from the eruption, trying to comprehend what had just occurred. Satellite measurements revealed that the eruption had injected an unprecedented amount of water vapor into the stratosphere, an estimated 146 million tons. This was remarkable because volcanic eruptions typically inject sulfur dioxide and ash into the atmosphere, which cool the planet by reflecting sunlight. But Hunga Tonga's submarine nature meant it vaporized enormous quantities of seawater, and water vapor is a greenhouse gas. Climate scientists began investigating whether the eruption might actually cause temporary warming rather than cooling. Seismic data provided additional insights into the eruption's mechanics. The explosion had been so powerful that it registered as a magnitude 5.8 earthquake on seismometers worldwide. But the seismic signature was unusual. Unlike typical earthquakes caused by rock fracturing, this signal showed the characteristics of a massive explosion, a sudden release of energy that sent shockwaves through both the ocean and the Earth's crust. Underwater surveys conducted months later revealed that the eruption had fundamentally reshaped the volcano itself. The caldera had collapsed, creating a submarine crater over 850 meters deep. As the scientific community analyzed months of data from the Hunga Tonga eruption, one conclusion became inescapable. This was the most powerful volcanic explosion ever recorded by modern instruments. While larger eruptions have occurred in Earth's geological past, such as the 1815 Tambora eruption in Indonesia or the catastrophic Toba super eruption 74,000 years ago, those events preceded the satellite era and sophisticated monitoring networks. The Tonga eruption was the first time humanity had the technological capability to measure every aspect of such a powerful volcanic event in real time, from the initial explosion to the global atmospheric response, from the tsunami propagation to the reshaping of the seafloor itself. The eruption's volcanic explosivity index was calculated at VEI 5 to 6, placing it among the most powerful eruptions of the past century. But the VEI scale, which primarily measures erupted volume based on the total amount of material ejected, doesn't fully capture what made Tonga exceptional. It was the explosive power, the energy release rate measured in the span of minutes rather than hours or days, that set records. The combination of gas-rich acidic magma and catastrophic interaction with seawater created an explosion mechanism far more violent than typical subaerial eruptions like Mount St. Helens or even Pinatubo. To put the eruption's power into perspective, researchers calculated that the explosion released approximately 15 megatons of TNT equivalent energy in just the initial blast. For comparison, this is roughly 11 times more powerful than the atomic bomb dropped on Hiroshima and comparable to the largest thermonuclear weapons ever tested by major powers during the Cold War. But unlike a nuclear explosion, which releases its energy almost instantaneously, the Tonga eruption sustained its violence for several hours, with the most intense phase lasting approximately 12 hours and residual eruption activity continuing for days afterward. The acoustic energy alone was staggering. When researchers analyzed infrasound data from monitoring stations worldwide, they determined that the eruption produced the loudest sound recorded in the modern era. The atmospheric pressure wave, which as mentioned earlier circled the globe multiple times, carried an estimated 2.6 times 10 to the power of 18 joules of acoustic energy. To understand this scale, consider that the 1883 Krakatoa eruption in Indonesia, long considered the benchmark for explosive volcanic power and audible over 4,800 kilometers away, was estimated to have produced a comparable or possibly smaller acoustic signature based on historical accounts. The Tonga eruption matched or exceeded Krakatoa's acoustic power while being comprehensively measured by modern instruments. Volcanologists studying the event identified several critical factors that amplified the eruption's power to record breaking levels. First, the shallow water depth, with the caldera sitting just 150 meters below the ocean's surface, meant seawater could interact with magma efficiently while still providing enough confining pressure to prevent gradual degassing. This created what's known as optimal depth for phreatomagmatic explosions. If the volcano had been deeper, the water pressure would have suppressed explosions. If it had been shallower or above sea level, the confinement effect would have been reduced. Hunga Tonga sat in the Goldilocks zone for maximum explosive potential. Second, the rapid ascent of fresh gas-rich magma from the deep magma chamber, located approximately 5 kilometers below the seafloor, didn't allow time for pressure equilibration or degassing through preliminary eruptions. Petrological analysis of erupted material revealed that the magma contained extremely high concentrations of dissolved volatiles, particularly water vapor and carbon dioxide, which had been kept in solution by the immense pressure at depth. When this magma suddenly ascended and pressure dropped, these gases exhaled explosively, like opening a shaken champagne bottle but on a geological scale. Third, the caldera's geological structure created a natural pressure vessel. The overlying rock layers and seawater acted as a cap, containing rising gases and building pressure until the system reached its failure point. When that threshold was exceeded, the entire cap failed catastrophically rather than gradually, releasing all the accumulated energy in a single violent pulse. This is fundamentally different from many subaerial volcanoes, where gases can escape through fumaroles and vents, allowing pressure to release incrementally. The unprecedented injection of water vapor into the stratosphere also set the Tonga eruption apart from any other volcanic event in the modern record. Scientists calculated that the eruption lofted approximately 146 million tons of water vapor into the stratosphere, increasing the total water content of the stratosphere by roughly 10%. This was 5 times more water vapor than any other eruption in the satellite era. The mechanism was straightforward but extreme. The eruption vaporized a volume of seawater estimated at 0.15 cubic kilometers, then injected this superheated steam upward with such force that it penetrated the tropopause and entered the stratosphere where it would normally never reach. This stratospheric water vapor injection had immediate and measurable effects on Earth's climate system. Unlike sulfur dioxide, which reflects sunlight and causes cooling, water vapor is a greenhouse gas that traps heat. Climate models run by NASA and other institutions predicted that the Tonga eruption might cause a temporary warming effect of approximately 0.01 to 0.03 degrees Celsius over the following 1 to 2 years, the opposite of what volcanic eruptions typically produce. While this might seem small, it was detectable against the background of ongoing climate change and represented an entirely new category of volcanic climate impact. This research has profound implications for volcanic hazard assessment worldwide. Scientists have identified dozens of submarine volcanoes in similar geological settings around the Pacific Ring of Fire, the Caribbean, and the Mediterranean that could potentially produce Tonga-scale eruptions. Many of these volcanoes are poorly monitored, with limited real-time surveillance networks. The Kikumjeni submarine volcano near Grenada, the Colombo volcano north of Santorini in Greece, and multiple calderas in the Mariana Arc all share similar characteristics. Shallow submarine calderas, evidence of past explosive eruptions, and locations along active subduction zones. The eruption also demonstrated that submarine volcanoes can generate far-reaching hazards that bypass or overwhelm traditional warning systems. The Medio tsunami, generated by atmospheric pressure waves rather than seafloor displacement, arrived at some Pacific coastlines before traditional earthquake-generated tsunami warnings could be processed and disseminated. This represents a significant challenge for disaster preparedness. Current tsunami warning systems are optimized for seismically generated tsunamis, where the initial earthquake provides minutes to hours of warning time. Volcanic tsunamis, especially those enhanced by atmospheric pressure waves, can arrive with little to no advance notice. In the aftermath of the Tonga eruption, international scientific organizations, including the Global Volcanism Program, the International Association of Volcanology and Chemistry of the Earth's Interior, and various national geological surveys have called for enhanced monitoring of submarine volcanoes worldwide. Proposals include deploying more seafloor pressure sensors, expanding satellite monitoring capabilities, and developing new models specifically designed to forecast phreatomagmatic eruptions. But perhaps the most important lesson from Hunga Tonga is this: Earth's most dangerous volcanoes might not be the ones we can see. While attention naturally focuses on towering stratovolcanoes like Mount Fuji, Mount Rainier, or Popocatépetl, the hidden calderas beneath the ocean possess the potential to unleash explosive power that exceeds anything witnessed in the modern era. The Tonga eruption proved that these submarine systems can produce explosions rivaling the largest volcanic events in human history, generate global-scale atmospheric disturbances, and create cascading hazards that affect distant coastlines thousands of kilometers away. What's your opinion about this unprecedented volcanic event? Let us know in the comments below.